Welcome to Spring LIB.
7.91. So we have a mass on a rope that's attached to a ceiling or something, and we have a force that's always acting perpendicular to the rope that the mass is on that lifts it up to some height, h, and we want to show that the work that this force does is equal to just the work of lifting the mass a height h. And we're given a hint that when the angle is changed by d theta in radians, the arc length along which the mass moves, so along the sort of circle here, is L d theta. And this basically just follows from the definition of an angle, which is the arc length along a circle subtended by that angle divided by the radius of the circle. So d theta is ds over L, or ds equals L d theta. So we have this force. We also have the weight of the little mass here. And this is done without the mass accelerating. We also have a force of tension. And at any point along this, this path that it's taking, we can imagine we have an x and y directions. The actual orientation of these changes as you increase the angle or decrease the angle, but for convenience, let's just think of them as x and y. So the sum of the x forces, we have F acting in the positive x direction, and then we have a component of the x component of the weight that ends up acting in the negative x direction. This is mg sine theta. And because it's not accelerating, this has to be equal to 0. So the force is mg sine theta. So far, so good. Now the work that this force does will be the integral. Well, let's not worry about the limits just yet, of f dot dl, or ds, whatever. Let's call it ds, actually, because L already has a use in this problem as a constant. And so we know that ds is L d theta. So we can integrate this from 0 to theta 0 here. We have theta naught is the angle to which this is moved that corresponds to increasing the height by h. So we have f times the cosine of 0, because f is in the same direction as ds, L d theta. And so this is mg L times the integral from 0 to theta naught of sine theta d theta. Now this is mgl, and just evaluating the integral and its limits of integration, we get a 1 minus cosine theta naught. And so this is looking good, assuming that L times 1 minus cosine theta naught is equal to h. So let's think about the geometry there for a second. We have our ceiling. We have the length of the rope that forms the radius of this circle. Actually, I guess the yeah. Just erase this. Mass needs to be on the actual circle there. Okay. So this angle here is our theta naught. This line here also has a length of L. So this distance here is L times the cosine of theta naught. So if L is the total, and here this is H as set up in the problem, and so if this total length here is L, and this is L cosine of theta, then H is going to be L minus L cosine theta equals L1 minus cosine theta, just factoring the L out. And so we see that this is actually H, so that's good. Because now we're done. We've shown that this is the same as the work you'd need to just lift the mass by a height H.